Hello, AP Chemistry students. We're now at Unit 8, Part 2, and this is going to be on buffers and titrations. And it's going to cover sections 8.5 and 8.7 through 8.10. So our learning objectives here are to explain the results from the titration of a mono or polyprotic acid or base solution in relation to the properties of the solution and its components, to explain the relationship between the predominant form of a weak acid or base in a solution at a given pH and pKa of the conjugate acid, or pKb of the conjugate base, to explain the relationship between the ability of a buffer to stabilize pH and the reactions that occur when an acid or base is added to a buffered solution, to identify the pH of a buffer solution based on the identity and concentrations of the conjugate acid-base pair used to create the buffer, and to explain the relationship between the buffer capacity of a solution and the relative concentrations of the conjugate acid and conjugate base components of the solution. So last time we talked a bit about neutralization reactions and how to calculate the pH of a solution after an acid and base are mixed. And how you approached this was largely dependent on what was in excess at the end, whether it was an acid in excess or a base in excess. And I made a caveat about the ones where the weak acid or weak base was in excess, because you have to consider the equilibrium. You need to consider what has been dissociated, whether there are conjugates in solution that are going to interact with water. There's a lot more variables when the weak acid or weak base is in excess. But today we're going to talk about how to deal with that. And there's a specific equation that is used to calculate the pH of a solution when an acid or when a weak acid or weak base is being used. And it's called the Henderson-hasselbalch equation. And in this equation, it generally takes the format of pH equals pKa of an acid plus the log of the ratio of the conjugate base over the acid, both being concentrations. And if we're looking at a base being in excess, we would use POH is equal to the pKb of that base plus the log of the conjugate acid concentration over the original base solution. Or not the original base solution, but how much of the unprotonated base there is at the point in time that we're looking at. And we need to know the ratio of the acid base or conjugate acid base and the pKa and pKb in order to figure out the pH or the POH. There's also a shortcut version of this equation. This equation is not, or this version of the equation is not going to be on your equation sheet. But since we have pH is equal to pKa plus the log of the ratio of, in this case, the conjugate base over the acid, all of these are logged. So if you remember that log property where the log of two things multiplied by each other is equal to the log of the separate additions of those two things, you could sort of apply that logic in reverse so that instead of being plus these two things, it's going to be multiplied by all of these things. So it's going to be the unlogged Ka times the unlogged ratio of the conjugate base over the acid. But since this was a negative log and this was a positive log, that ends up flipping the ratio. So just note that in this shortcut version, we have the hydrogen ion concentration is going to be equal to the Ka times the acid over the conjugate base, whereas the ratio in the original Henderson-hasselbalch equation was conjugate base over acid. And likewise for the POH, we can undo the log and end up with the OH minus concentration is equal to Kb times the base over the conjugate acid. And if you use this shortcut, there will be one extra step to calculate pH or POH, obviously, because we're just solving for the hydrogen ion concentration or the hydroxide ion concentration. So that final volume will need to be negative logged. All right, so let's try an example of this. Let's calculate what the pH of the final solution when 75 milliliters of 0.1 molar acetic acid is mixed with 25 milliliters of 0.1 molar sodium hydroxide. Now, we can already tell from the numbers given, they both have the same concentrations, but the concentration of the acetic acid, the weak acid in this case, is, or the volume is 3 times more than the volume of the base being added to it. So we can basically already see that the weak acid is going to be in excess here. So we're going to want to use the Henderson-hasselbalch equation. And how that's going to work, first we need to calculate the available moles of each substance. So for the acetic acid, it was 0.1 molar, aka 0.1 moles per liter. We multiply that by 0.075 liters, and we end up with 0.0075 moles of acetic acid to start with. We do similar math for the sodium hydroxide and find out that we have 0.0025 moles of sodium hydroxide. So we have 3 times as much acetic acid in this reaction as we do sodium hydroxide. So that means the weak acid is definitely in excess. And since we're going to need to know the ratio of the weak acid to its conjugate base once the reaction has occurred, we're going to need to apply a little bit of logic here. So we know that we have 0.0025 moles of the hydroxide, and that is going to neutralize 0.0025 moles of the acetic acid by stealing the protons, by stealing the hydrogen ions and making water. So that means 0.0025 moles of this are going to be converted into conjugate base. This is going to leave 0.005 moles of the original acetic acid, unprotonated, left over. And like I said, it's going to produce 0.0025 moles of the acetate, of the conjugate base in this case. So now we can apply that to the Henderson-hasselbalch equation. We know we have 0.005 moles of the acetic acid in 0.1 liters, so that's going to be 0.05 molar acetic acid after the mixture of the acid and the base. And then the conjugate base is going to be 0.025 molar. So now I can plug this all in to the Henderson-hasselbalch equation. So the pH is going to be equal to the pKa plus the log of the conjugate base over the acid concentrations. So that's going to be negative log of the Ka, which we got from the setup, plus 0.025 over 0.05. And that's going to give us pH is equal to 4.74 plus negative 0.3. And the final pH of the solution is going to be 4.4. Now, if we use the shortcut version instead, the hydrogen ion concentration would be equal to the Ka of the acid over the conjugate base. And that's going to be 1.8 times 10 to the negative 5 times 0.05 over 0.025. Remember, it is flipped upside down now here. That's going to give us 3.6 times 10 to the negative 5 for the hydrogen ion concentration. And then to turn that into a pH, we just negative log it at the end, and we end up with 4.4. So we get the same answer by using the shortcut method. So just as a reminder, the shortcut method is not going to be on your equation sheet, so you're going to have to apply a little bit of logic to get to it, or just memorize what that version of the equation looks like. But as you saw, the normal Henderson-hasselbalch equation got us to the same answer, and the Henderson-hasselbalch equation is on your equation sheet. All right, let's try another one where we have a weak base, ammonia, with 100 milliliters and a 0.4 molar solution. And we're going to mix that with 40 milliliters of 0.5 molar hydrochloric acid. So now we're mixing a weak base with a strong acid, and we can kind of already tell from the numbers that the weak base is going to be in excess. And we have a Kb for ammonia of 1.77 times 10 to the negative 5. So we can apply a similar process here. We can take our ammonia, we take the concentration, multiply it by the volume. We end up with 0.04 moles of the ammonia before the mixture happens. For the hydrochloric acid, we have 0.02 moles of hydrochloric acid. And then when we apply that sort of stoichiometry logic, we can infer that there will be 0.02 moles of the ammonia left, because 0.02 moles of acid is going to donate hydrogens to the ammonias, making ammonium. And we're going to produce 0.02 moles of ammonium in the reaction. So at the end of the reaction, we're going to have an equal amount of ammonium and ammonia and then ammonium ions, both going to be 0.02 moles. And if we divide that by the total volume, which is now going to be 100 plus 40, so 140 milliliters, so we divide that by 0.14 liters, and we can see that the concentration of both ammonia and ammonium are going to be 0.143 molar. So now we can plug this in to the Henderson-hasselbalch equation to get the POH. So the POH is going to be equal to the pKb plus the log of the conjugate acid over the base. The pKb is going to be the negative log of the Kb, which is 1.77 times 10 to the negative 5, plus the log of the ratio, which is going to be 0.143 over 0.143. So this is just going to be 1. And the log of 1 is actually 0. So this second term in the equation is just going to be 0 and basically cancel out. So the POH in this case is just going to be equal to the pKb, which is going to be 4.75, aka 4.8 rounded to 2 sig figs. And if we apply the shortcut method, the hydroxide ion concentration is going to be equal to the Kb times the conjugate acid. It's going to be the base over the conjugate acid since the ratio is flipped. Oops. And that's going to be 1 again. So basically, the hydroxide ion concentration is going to be equal to the Kb. And if we negative log it, we're going to get 4.8 again. So we're going to get the exact same answer for the POH. And say we wanted to know what the pH of this solution was, we'd apply the logic that we've used in the previous video, where the POH plus the pH is equal to 14. So we can subtract the POH from 14 and get 9.2 for the pH of the final solution here. And I set up this equation, or I set up this problem to have the ratio be 1 on purpose, because this shows us something important about mixing acids and bases. When the conjugate acid and base, or the conjugate base and acid are in equal proportions, the second term ends up becoming 1, and the log of 1 ends up becoming 0. So that means when the acid or base and its conjugate are in equal proportions, the POH or the pH is going to be equal to the pKb or the pKa. And this is actually going to be really important later. You'll see why in a bit. All right, so due to the presence of conjugate acid or base in a weak acid or base solution, we'll note that the pH will not change very quickly as it would for a strong acid or strong base solution. And the reason for that is because of conjugates. So if we consider the following reaction of hydrochloric acid reacting with ammonia, like the last problem, that will make ammonium and chloride ions. So that means when we add hydrochloric acid to this solution, it's not going to increase the amount of hydrogen ions and therefore decrease the pH, because those hydrogen ions are going to be donated to NH3 to make ammonium, since the base is accepting those hydrogens and basically pulling them out of solution into themselves. And this is a property of weak acids and bases that can be utilized if we want the solution to resist pH change. A solution that can resist pH change is called a buffer. And a buffer is created when you're preparing a solution of weak acid or base along with a near equimolar amount of its conjugate as a salt, like we saw in that problem where the amount of the amount of base and conjugate acid were the same. And we ended up with a pKb equal to the POH. And for example here, say we had a solution of acetic acid and we mixed that with sodium acetate, which after dissolution would just be acetate ions. This would make a great buffer. And strong acids and bases do not work as buffers because their conjugates are too weak. Their conjugates are not going to be able to give up or accept protons or hydrogen ions. So for example of how this works, so say we're doing this acetic acid / acetate buffer where we have near equal amounts of both of these things. If I was to add a base to the solution, say I'm adding hydroxide ions, well, those hydroxide ions, instead of raising the pH by increasing the amount of hydroxide in the solution, it's going to interact with the weak acid and take its protons and basically turn it into water. It's just going to neutralize it. So instead of the hydroxide ion concentration going up and the pH going up as a result, we're just going to form this conjugate base of the acid instead, which is not going to change the pH by very much. Now, if we were to add an acid, well, we also have a bunch of acetate in solution, the conjugate base of the acetic acid. Well, that is going to be a base because it's the conjugate base of the original acid, so it's going to act like a base. When we add hydrogen ions, it's going to absorb them, it's going to accept them, and turn back into more acetic acid. So in this case, the acid that we added to the solution is going to be neutralized by the conjugate base instead of lowering the pH. So in both of these cases, since we had a bunch of acetic acid and acetate in solution, neither the addition of hydroxide or hydrogen ions was able to change the pH of the solution because they both got neutralized by one of the substances that was available. So you might be wondering why we care about resisting pH change. Well, this is mostly for biological reasons. Most organisms are sensitive to pH change, and blood itself is a natural buffer. So when you respirate, you take in oxygen and produce carbon dioxide, and that carbon dioxide is dissolved in your blood. And when carbon dioxide is dissolved in an aqueous solution, it tends to form carbonic acid and the conjugate base of carbonic acid, which is also a weak acid in itself. And it's going to create these in a ratio that will control pH changes in the blood. For example, if we ended up with base in our blood, the carbonic acid would neutralize it by donating a hydrogen ion to it to produce the conjugate base and a water molecule. And then if acid was added, if hydrogen ions were added to the blood, the conjugate base of the carbonic acid would neutralize the hydrogen ion by absorbing it and making more of carbonic acid. So you can see in both of these cases, the added acid or base is neutralized by the buffer. So the best pair of substances to use as a buffer is going to depend on what pH you want to stabilize your solution at. So since we saw that the pKa is equal to the pH when an acid and its conjugate base are in equal concentrations, it's going to be best to use a substance with a pKa that is close to the pH you're trying to stabilize. Because at that point, you're going to have equal amounts of the acid and the conjugate base or the base and the conjugate acid that will be able to neutralize either added acid or added base. So say we wanted to figure out what pair we would use to stabilize something at a pH of 4.3. Say we had some sort of fish in an aquarium that liked acidic conditions. Well, if we look at this table here that lists the pKa of a bunch of substances, 4.3 is going to be close to here, 4.20 for benzoic acid. So that means to make a buffer that is stabilized at 4.3, we're going to want to make a solution that is a combination of near equimolar amounts of benzoic acid and its conjugate benzoate. And this is going to be a good buffer for a pH 4.3 solution. Now, there's also something called the buffer capacity, which is how effective that buffer is going to be. And we can adjust how effective it's going to be in a few different ways. So one general way to increase the capacity overall of the buffer, increase the amount by which it can resist pH change in either direction, would be by raising the concentration of both the acid and its conjugate, or the base and its conjugate, because that means there will just be more molecules in solution that can neutralize the added hydroxide or hydrogen ions. But say we also wanted to resist it more in one direction or the other, we could do that by messing with the ratio a bit. If the amount of acid in the solution is more than the base, the solution will be better at resisting bases because we'll have more acid available to do so. And vice versa, if the acid concentration is less than the base concentration, it's going to be better at resisting acids because we'll have more base available to neutralize the acid that's added. And for the benzoic example above, since the pKa is 4.2, but the pH is 4.3, which is a slightly more basic pH, we can assume that in this case, the base is going to be in higher concentration than the acid. So even though this solution is going to be a good buffer in either direction, it's going to be slightly more effective at resisting the addition of acid and the decrease of pH. So this next slide is going to be a little bit of a review. So back in section 4, or in unit 4, we talked about titrations. And we talked about how acids and bases can be used to solve for unknown concentrations of each other by slowly adding one with a known concentration to a solution with an unknown concentration. And like I said, this is called a titration. And the common setup for titration usually involves a solution with your unknown acid or base, and then a burette, like a tall, skinny tube with lots of graduations on it that you can slowly measure the amount of volume that is being added. And then usually in the solution, you're going to have either a pH meter that is going to be detecting when we've reached an equivalence point, when the concentration of the acid and the base have become equal, or something called an indicator, which usually has a color change associated with it, that will help us figure out when it is switched over from being an acidic solution to a basic solution, or vice versa. Now to talk a little bit more about indicators, these are usually hydrocarbon-based chemicals, meaning they're made of carbon and hydrogen, and usually some oxygens or nitrogens or things like that. And these can act as a weak acid and will generally change colors when they lose protons. A very common example of this is an indicator called phenolphthalein, which usually goes from a colorless solution to a pink solution when it is in excess of base. And we can see on this chart, phenolphthalein here, you can see it's going to be colorless until it reaches basic conditions when it turns pink. Phenolphthalein is usually used in lots of titrations where you're trying to detect when it reaches pH 7, because once it goes beyond pH 7, it's when it starts to turn pink. And the color change is usually observed when the acid and the conjugate base are in equal proportions, which we also know means when the pH is equal to the pKa. So when you're planning a titration experiment, you're going to want to pick an indicator that has a pKa close to the equivalence point of the titration that you're trying to do. Remember, the equivalence point is when the unknown acid is going to be equal to the concentration of the base that you added, or vice versa. So when a strong acid is titrated with a strong base, or vice versa, the data can be graphed to show this relationship. So this is called a titration curve. We can see on both of these graphs, we have pH as our y-axis, and then the volume of what's being added, the volume of what's called the titrant. And in this case, we have a acid that is being titrated with a base, because we can see that it starts at low pH, and then the pH rises until we reach 7, where we see an inflection point, and then it starts to go higher than 7 once we've reached totally basic conditions. And this inflection point is really important. This is called the equivalence point. And like I mentioned earlier, this is when the amount of acid and base are equal. And please note that I'm not talking about the amount of acid and its conjugate base, or the amount of base and its conjugate acid. I mean the amount of acid you started with, and then the amount of base that you added to the solution. And this point is really important because we can use the volume of the titrant added at this point to solve for the concentration of the unknown by figuring out how many moles we added, because at that point is usually going to be a 1-to-1 ratio of the moles of the known and the moles of the unknown. So from there, we can infer the concentration of the original solution. And I didn't talk about the base graph, but you can see that it has the opposite shape. We start at a high pH because it's basic. The pH is going to be decreased until we reach pH 7 when it's neutralized, where we have the inflection point, and then it starts to go to the lower pHs. And the big reason why these are curved is because pH and pOH, if you remember, are logarithmic. So the relationship between like 7 and 8 or 7 and 6 is going to be less than the relationship between like 6 and 5, for example. So that's why we have sort of an exponential effect here. So here's just a quick calculation example. Say we have 50 milliliters of a hydrochloric acid solution with unknown concentration that we're going to slowly titrate with 2.0 molar sodium hydroxide in order to determine the concentration of the hydrochloric acid. Now we can see here on the graph that we reach the equivalence point at a pH of 7 at around 25 milliliters of base being added. So in order to figure this out, either you're going to need to know how much needed to be added to get to the equivalence point, or have a graph or a table to reference. Now, we know that the sodium hydroxide is 2 molar. So if we do 2 moles per liter times 0.025 liters, that means that 0.05 moles of the sodium hydroxide were added to the solution. And since this was the equivalence point, we know that there was also 0.05 moles of the acid in the original 50 milliliter solution. So from that, we can infer that there was 0.05 moles in the original solution, and the total of 50 liters. That means that the original solution of hydrochloric acid was 1.0 molar. So those graphs that we just looked at, those apply to the titrations of strong acids or bases. When we look at the titration of weak acid or bases, we see a slightly different type of graph. And this is because of buffering. We know that a weak acid or a weak base will behave as a buffer when it's in equal proportions to its conjugate. That means there's going to be a region on the graph where the pH is going to not change very much. For example, see here we have sodium hydroxide being added to acetic acid, which is a weak acid. We start at a low pH, and then there's this portion here where it kind of flatlines for a bit, where the addition of a bunch of this base doesn't change the pH very much. And we call this the buffering region. And you'll see that that doesn't really exist on strong acid and strong base titrations. It just kind of has this consistent exponential curve to it. So this buffer region also has an important point in it. So our equivalence point was when our acid and our added base, or our base and our added acid, are in equal concentrations. And there's another point in the middle of the buffering region called the half equivalence point, or midpoint. And this is where the original acid and its conjugate base are in equal proportions, or an original base and its conjugate acid are in equal proportions. And this is also where the pH is equal to the pKa, or the pOH is equal to the pKb. You'll also note that on this titration graph between a strong base and a weak acid, that our equivalence point is not at 7 like it was in the strong acid and strong base graphs. And this also has to do with the conjugates. You can see that the equivalence point for this acetic acid solution is actually above 7. And the reason for that is because you're adding strong base. The hydroxide is going to be pulling the hydrogen ions off of the acetic acid. And once we have gotten to our equivalence point, when we've added enough sodium hydroxide to neutralize all of the hydrogen ions from the acetic acid, what we're left with is water molecules and acetate. And acetate is the conjugate base of acetic acid. So that means that the only ion left in solution at that point is a conjugate base, which is going to behave like a conjugate base, interacting with the water and making hydroxide, which was going to make the pH at this point slightly basic. If we look at a graph for a weak base and a strong acid, sort of the opposite of the last one, we're going to see that we see the same effect, but just kind of flipped upside down. We start at a high pH. It lowers a little bit as we add acid, and then we reach a buffering point, or a buffering region, which has a midpoint where our pOH is equal to our pKb. And then after the buffering region is gotten through, the pH starts to lower again, where we get to an equivalence point around here. It's around like 5 or so. So we could see, much like the last time, the equivalence point is not going to be at 7 when a weak acid or weak base is involved. In the case of the weak base, at this point, the only ion left in solution is the conjugate acid of the weak base, and that's going to do conjugate acid stuff. It's going to interact with the water molecules and make hydronium, aka hydrogen ions, and make the overall solution acidic instead of neutral. And sometimes you'll deal with a polyprotic acid, something like carbonic acid, sulfuric acid, or phosphoric acid. Polyprotic meaning it has multiple hydrogens that can come off. Even though sulfuric acid, I mentioned this before, even though sulfuric acid is a strong acid, that only includes the first hydrogen. the HSO4 minus that occurs after that first hydrogen ion comes off is a weak acid. And carbonic acid and phosphoric acids are both weak acids. So all three of those are going to have buffering regions in their graphs. But you'll also see that there's sort of a cycle that repeats. So for example, we could call this a carbonic acid solution. So we'll start here with H2CO3. And then as we start to titrate it with a strong base, we reach our first buffering region and we get to our first midpoint. And at this midpoint, the amount of carbonic acid is going to be equal to the amount of its conjugate base, and the pH is going to be equal to the pKa. And then once we get out of the buffering region, it's going to shoot up again where we reach our first equivalence point. And this is where all of our H2CO3 has been converted to HCO3 minus, aka the moles of base being added are equal to the concentration of the original, or the amount of moles are equal to the amount of moles of the original carbonic acid in solution. But since this is polyprotic, we have to go through another cycle of titration because we have another hydrogen ion to remove. So as we continue, we reach a second buffering region where the HCO3 minus is interacting with hydroxide ions to produce pure carbonate, CO3 2 minus, by taking off the hydrogen ions here. And at this second midpoint, in the middle of the second buffering region, that's where the HCO3 minus is going to be equal to the CO3 2 minus, and the pH is going to be equal to the pKa of the conjugate base of the original carbonic acid, which, like I said before, is also an acid itself because it has a hydrogen ion associated with it. And it's a quick tangent. We talked about this in previous lessons, but something that can behave as both an acid and a base is called amphoteric. And HCO3 minus is amphoteric because it can gain a hydrogen like a base and become H2CO3, or it can give up a hydrogen like an acid and become CO3 2 minus. Very often, the middle states of the polyprotic acids are amphoteric. So that was a tangent. Back to what I was saying. At the second midpoint, this is where our HCO3 minus is equal to our CO3 2 minus. And this is going to continue through the cycle, and it's going to reach a second equivalence point. And this is where all of the HCO3 minus is going to have been converted to CO3 2 minus. So this is the point where the amount of hydroxide being added to the solution is going to be equal to twice the amount of H2CO3 that there originally was because of the fact that there are 2 protons per every molecule. And at that point, all of the hydrogen ions have been used up. And kind of like I mentioned, the Ka for each of the stages of the acid, depending on what point it's in its deprotonation, are going to be different. Like HCO3 minus is obviously going to have a different pKa than H2CO3, for example. So now let's use what we've learned to describe what's happening in this graph. So in this graph, we can see that it starts at a high pH, which means that we are starting with a basic solution. So we can infer that since the pH is going down, that we have been adding an acid to the basic solution. We can see it has a buffering region, which means that this base is a weak base. And we can see that the buffering region is around pH 10-ish. So that means that where the pH is 10, the pOH is going to be 4, and the pKb is also going to be around 4. So from this graph, we could also calculate the Kb of this base. And we can also see that there's an equivalence point, probably around 5. This is just another evidence for this being a weak base, because once the weak base has been fully reacted, it's going to have a conjugate acid left over in solution, which is going to make the overall solution slightly acidic at the equivalence point. All right, so now let's put all of these concepts together and show how we can do some calculations involving titrations of weak acids and weak bases. So let's start with this example where we have 200 milliliters of 0.225 molar hydrofluoric acid, aka HF, and we are titrating it with 0.115 molar sodium hydroxide. And we know that the Ka for hydrofluoric acid is 6.6 times 10 to the negative 4. So this is going to be a multi-stage question. The first part we want to answer is what volume of sodium hydroxide is required to reach the half equivalence point and the equivalence point. So for the half equivalence point, we're looking for the point in the titration in which half of the moles of HF have been converted to F minus. So I take my moles of HF, which are 0.045, and divide that by 2, which means that at this point, we'll have 0.0225 moles of HF left, and we will have formed 0.0225 moles of F minus. And since the HF to NaOH is a 1-to-1 ratio, that means that we will have also added 0.0225 moles of sodium hydroxide to get to this point. And since the concentration of the sodium hydroxide is 0.115 molar, we can use that with the moles of sodium hydroxide to calculate the volume by dividing by the concentration. And then we end up with 0.196 liters, aka 196 milliliters, to get the solution to the half equivalence point. Now for the equivalence point, this is going to be when all of the HF has turned into F minus. So the amount of sodium hydroxide is going to be equal to the amount of HF that was in the original solution. So since we started with 0.045 moles of HF, we're going to need 0.045 moles of sodium hydroxide to get there. So then I can use that divided by its concentration, and that gives me 0.391 liters, aka 391 milliliters of base added to get to the full equivalence point. All right, now for part B of this question. In a titration of hydrogen fluoride or hydrofluoric acid, what is the pH at the half equivalence point and the equivalence point? One of these is going to be easy and one of these is going to be tricky. So let's have a look at this. So for the half equivalence point, I've already mentioned a ton of times in this video, at the half equivalence point, the pH is going to be equal to the pKa. So all we need to do is take the Ka of the hydrofluoric acid and negative log it, and we'll end up with, in this case, 3.18. So this is going to be the pH when we're at the half equivalence point. Now for the equivalence point, there's a lot to talk about here in terms of the logic of this situation. So we know at this point all of the HF has been converted to F minus, and this means that we're going to need an equilibrium expression because we don't have any hydrogen ions left in solution. All we have is a conjugate base, and we can figure out what the pH is going to be based off of knowing what kind of chemistry the conjugate base is going to do. So we know that we have 0.045 moles of F minus at this point. We've also added 391 milliliters of the base, which we calculated in the last problem. And there was originally 200 milliliters of the analyte solution, of the original HF solution, which means the volume at this point in time is 591 milliliters. So from that, I can calculate the concentration of F minus by dividing the moles by the liters, and we end up with a concentration of 0.0761 molar. And since we need to figure out what the conjugate base is doing at this point, we're going to need the Kb of the conjugate base. So if you remember from the last lecture, the way we do this is based off the expression that Ka times Kb is equal to Kw. So if we divide Kw by Ka, we can solve for Kb for F minus, the conjugate base of the original acid. So Kw at room temperature is always 1 times 10 to the negative 14. So we divide that by 6.6 times 10 to the negative 4, and that gives us a Kb for our conjugate base of 1.52 times 10 to the negative 11. Now, what we do with this is we need to set up an equilibrium expression, because we know that when the F minus is on its own, it's going to act as a base by interacting with the water in solution, and the F minus is going to react with H2O to make more HF and hydroxide. So like we mentioned before with the weak acid titrations, at the equivalence point, the pH is going to be above 7 due to the conjugate base producing hydroxide. So if we want to know the pH, we can actually solve for it by calculating the pOH and then subtracting it from 14, because at this point, hydroxide is the more relevant ion. So I set up my Kb expression, the HF times the hydroxide ion, over the concentration of the conjugate base, which we just calculated as 0.0761. The amount of HF and the amount of hydroxide ion are going to be equal to each other based off of the mole ratio. And we set that equal to our Kb. And in this case, our X, aka our hydroxide ion concentration, is going to be 1.07 times 10 to the negative 6, which we can negative log to get the pOH, which will be 5.97. And therefore, the pH at the equivalence point is going to be 14 minus the pOH, and the pH is going to be around 8. All right. So now let's say we add some random amounts of sodium hydroxide. Let's check in on what the pH would be at different stages in the titration. So not any of those points that we laid out earlier, like the half equivalence point or the equivalence point. Say we wanted to know what the pH was going to be after we added 80 milliliters of sodium hydroxide, and then what the pH was going to be after we added 300 milliliters of sodium hydroxide. One quick point we can at least make here, we can sort of estimate at least the vague volumes that are going to be involved here. We can see that this is before the half equivalence point, since the half equivalence point involved, what was it? 196 milliliters. So the pH is going to be lower than the pH at the half equivalence point. And the other volume that we're looking at here is 300. That is more than the half equivalence point, but less than the equivalence point. So the pH is going to be in between those two. But to get the actual concentrations of these, we're going to apply the Henderson-hasselbalch equation. So let's do the 80 milliliter example first. So if we had 80 milliliters times the concentration of the sodium hydroxide, that's 0.0092 moles of sodium hydroxide added. At this point, since they neutralize in a 1-to-1 ratio, that means that 0.0092 moles of the HF are going to be converted into F minus. So that means that our F minus concentration, or our F minus moles, are going to be 0.0092. And then to figure out how much of the HF is left, we're going to subtract 0.0092 from 0.045, because that'll tell us how much of the HF was left over, which is 0.0358. And in this case, I'm using just the moles. I don't really care about the volumes, because in most of these cases where we're using the Henderson-hasselbalch equation, we're dividing two things, two concentrations that are in the same solution that are going to have the same volume. So if we're dividing two ratios that have the same denominator, those denominators are going to cancel out in the first place. So I don't even really need to consider the volumes of the solution at this point. So here I set up my shortcut Henderson-hasselbalch equation, where the hydrogen ion concentration is equal to the Ka times the HF over the F minus, the acid over its conjugate base. That's going to be 6.6 times 10 to the negative 4 times 0.0358 over 0.0092. And we end up with a hydrogen ion concentration of 0.00257 molar, which we can then negative log. And that tells us that our pH at the 80 milliliter point of our graph is going to be 2.6. Now we're basically going to apply all of the same logic for the 300 milliliter example. We're going to calculate first how many moles of sodium hydroxide were added using the volume and the concentration. And then we know that 0.0345 moles of the HF are going to be converted to F minus. So that's going to be my F minus moles in the equation. And then I can subtract 0.0345 from 0.045 to get the amount of HF left, which will be 0.0105. And then I can do all the math. I end up with 0.000201 molar hydrogen ion concentration, which I can then negative log to get a pH of 3.7. All right, and while we're talking about HF, how would we make an HF buffer that is stabilized in the buffering region for HF? And let's also figure out what pH this buffer would be effective at. Well, I mentioned before that the best way to make a buffer is to combine near equal amounts of the acid and its conjugate base, or vice versa if you're looking at a base buffer. So that means we can add like sodium fluoride or potassium fluoride, something like that, some sort of ionic compound that has the conjugate base as its anion. So we would add a near equal amount of NaF to the original amount of HF in solution. It doesn't really matter what the cation is here. It's just going to be a spectator ion in the solution. And if we remember, the buffering region is sort of centralized at the half equivalence point when the pH is equal to the pKa. So if I calculate the pKa using the Ka by negative logging it, we'll get the pH in which the buffer is most effective. And that in this case, it'll be 3.2. All right, and also say we made a buffer solution. And say we made one that was 100 milliliters with a concentration of 0.320 molar HF and 0.380 molar sodium fluoride. So say this is a buffer where we wanted it to resist the addition of acid more. Let's calculate the starting pH of this buffer. For this, we can also use the Henderson-hasselbalch equation. Once again, I have used the shortcut version. So the Ka times the HF over the F minus. And I can just plug in the concentrations directly here since they've just been added to the same solution and they're not really reacting with each other. So 3.2 over 3.8, the HF over the F minus times the Ka, that gives me 5.56 times 10 to the negative 4. And I can then negative log that, and I get 3.25 as my pH for the buffer. And that is all for Unit 8, Part 2. And this is the end of Unit 8, so I'll see you in Unit 9.